Now, we are going to see how a polymers moves from an electrical insulator to an electrical conductor. These are organic molecules. Polymers are organic molecules made of carbon, hydrogen, nitrogen, oxygen, like those, with covalent bonds. Now, materials with covalent bonds are not supposed to be electrically conducting, because there is no availability of free electrons. So, these are not conductors. But you think now this brain, our brain, this is a biological molecule made of biological molecules. Our neurons, these are all biological molecules, but how these neurons are transmitting electrical signals and pulses, say beating heart, myocardial heart, there you can measure some electric pulse, where from that electric pulse is generated and that electric pulse is communicated, transmitted from one location to the other location. That means, organic molecules can also transmit this electricity or current, something like that, although there is no free electron. That means, there is some sort of mechanism or system is available which can provide this electrical conduction. Somehow this concept came in the mind of scientists in around before say in around say 1960s and say 65, like that, means in 60s. People started this research in research with these conducting polymers or organic conductors or organic semiconductors from 1970s, 70s, the last decade or last century. Now, you see, if you find some free electron available, it is a very fundamental concept. In metals, there are free electrons, that is why they are conducting. So, if we can make some electrons to remain free in polymer molecules, it can also conduct electricity, it is supposed to conduct electricity, and that we can call as synthetic metal, synthetic metal. Organic molecules can be considered as synthetic metal, organic molecules containing free electron or free electron devices there which can conduct electricity can be considered as synthetic metal. Now, there is a journal today, of course, high rank journal, the synthetic metal, they publish very fundamental works or good works, research works, synthetic metals. What is this? Now, you see pi electrons in molecules, these pi electrons are labile, they get delocalized, pi electron clouds. Now, if these pi electron clouds can be exploited for such conduction, then we can get electrical conductivity in conducting polymers. If delocalized or delocalizable pi electrons can be exploited in organic molecules, we can make them conducting electricity, which can behave as inorganic semiconductors. We can make device like p-n junction, electronic devices, can make defect free electronic devices, or electronic devices contain some defects, because semiconductors are called defective materials. Intrinsic semiconductors pure, they have certain conductivity, you put some defect, either you add some donor or acceptor which takes electron from the system or donates electron to the system, and that way it creates certain defect in materials, and that helps in conducting electricity known as semiconductor. Now, that concept has been extended with polymer materials also. Today, these polymeric semiconductors are making a revolution in electronic industries, in microelectronic devices. So, we can have some exposure to these conducting polymers or semiconducting organic semiconductors. What are these things? You have, you know, ethylene molecule, you know, there is a pi electron, there is a pi bond. Now, if you think that ethylene molecule is used to synthesize polyethylene, you know, once you react this ethylene molecule, it forms a macromolecule polyethylene, that pi electron cloud is consumed. In polyethylene there is no pi electron cloud, but if we can make a polymer from ethylene, hypothetically, if we can make a polymer of ethylene, like this, hypothetically, we do not know what is that molecule. So, if this pi bond repeats, like this, theoretically one can think, you see, we do not know from where we can make it, but at least I can draw on a piece of paper that if we can make a design of such a molecule, then we find there is alternate single bond, double bond, single bond, double bond. That means conjugated pi electron device, pi electron molecule. That means if you have a skeleton, say carbon skeleton like this, over this carbon skeleton, if we can develop like this, that means a delocalized system of electrons over this central skeletal molecule, then it can help in electric conduction. If there are such conjugated system of pi electrons, that means it can provide a cylinder of delocalized your electron cylinder of delocalized electrons, or delocalized electron cylinder. Our purpose is served. Ideally at least we can think. In reality, we have to see how far we can achieve, that is different thing, but ideally we can think that we can have a pi electron cloud over a skeleton carbon chain. That can be an ideal conducting polymer or semiconducting organic semiconductor molecule.
If you make the polymer of acetylene, then
Who told you acetylene? I do not know what is acetylene. Do not jump on that. My point is that today you have some prior information, you could say it acetylene, polyacetylene. When this concept came to the mind of scientists, for which people got Nobel Prize, that time people did not know. Actually, I am telling you the genesis. You can have your key idea like this. You can think of a new molecule over which, if you can design a pi electron cloud or electron cylinder, then our purpose is served. Now, actually, see this type of, you are right, this type of system, this represents polyacetylene, because acetylene has got 1 sigma 2 pi bonds, but it is difficult to polymerize. It cyclizes. It cyclizes to form benzene. Okay. But if sufficient and your adequate and appropriate conditions are supplied, then it can form a polymer, polyacetylene of high molecular weight. Polyacetylene of high molecular weight is a good conductor. Okay. Now, let us see here. You see, conducting polymers are unique as possible substitute for metallic conductors and semiconductors. Conducting polymers exhibit highly reversible redox behavior and the unusual combination of properties of metals and plastics. You see, redox behavior, you see, this is very important, redox behavior, for which the mechanism of conductivity is dependent, the way how it becomes conducting. That means, it is the donor and acceptor system. A substrate is there, to the substrate if something is donated, some charge cloud is donated, some charge carrier is donated, or it is removed from the substrate, either it is donated to the substrate or it is removed from the substrate. In both the cases, the system becomes unstable or it starts flowing electron, and we get the conductivity, we visualize the conductivity. And by virtue of such properties, we can exploit that material for various applications, say sensing, electronic nose, electronic tongue, actuators, artificial muscles, those can be made from these things by such electron pushing or electron withdrawing. That means, it happens through redox behavior, either oxidation, reduction. In simple oxidation reduction, what happens? Either electron is withdrawn, taken out, or electron is given. So, it becomes either positive or negatively charged, that is a redox behavior. All right. Now, that you see, this redox behavior, oxidation reduction, this is not a very new thing, it is old thing, old concept. So, that old concept was thought say 200 years back. Now, it took such a long time to think of some organic molecule where it can also be exploited. This was actually meant for only metals. We know that only metals can show such type of behavior, such type of characteristics, which can accept electron or remove electron, give away electron. So, by virtue of that, it changes its your charges, either the positively charged or negatively charged, like that, monovalent, divalent, like that. This is also possible with polymer. Now, the quantum of charge depends on the extent of this oxidation or reduction process. So, these have unique conduction mechanism and good environmental stability in presence of oxygen and water. Again, we try to correlate with this. You see, there are many things, you see, it takes few hours or even more than few courses to discuss on these conducting polymers, polymeric semiconductors, all these things. I am not going to that side. Yes, that can be done. I am not going to that side. The thing I want to tell you that these metals, by virtue of their oxidation reduction characteristics, they undergo electrochemical corrosion. That means, the stability of metals are at stake, is not it? Stability of metals are at stake. Today, we are trying to protect metals from their electrochemical corrosion, degradation, etc., by covering with something else, which is non-electrolytic. So, we try to cover metals with non-electrolytic material to protect the metals, that means they are unstable. We try to passivate the metals by putting some coating. We take aluminum is good metal, we take aluminum alloy. Why? Because aluminum is such a metal, it oxidizes eventually very quickly, forms some alumina Al2O3 thin film over aluminum metal, which passivates the aluminum. There is advantage. So, we try to use aluminum with other metal, so that presence of aluminum helps in passivation through aluminum oxide formation. So, we think of various techniques and devices to stabilize metal. Now, from there you try to understand the problem. The problem with metals is their reactivity, is their redox characteristics. So, we are asking for redox characteristics in polymer for getting conductivity. So, there is a failure in case of metals. Now, if we develop such type of reactivity in polymer for getting conductivity, again we are inviting that failure situation. What we should do? We should think of some polymer which will provide redox characteristics, but it should be stable. I tell you about the polyacetylene, the cause for which it provides you the conductivity, that becomes the reason for its instability. Once again, it is a chemical process, chemical reaction, chemical interaction, is not it? We need free electron for conductivity. If there is some free electron, it will not remain sitting idle. It will try to form bond with some other agent in the environment, meaning it is becoming unstable. So, these things should be kept in mind while thinking about this conducting polymer development, device making, all these things. So, these have unique conduction mechanism and good environmental stability in presence of oxygen and water. These polymers could be highly promising for many technological uses because of their chemical versatility, stability, processability and low cost. Now, if you think of inorganic semiconductor, you want to make some device, now you have to grow that crystal, which needs very sophisticated arrangement, sophisticated instrument. Well, in the laboratory for research purpose it is okay, but for commercial development of some semiconductor device, it cannot be economically feasible, price will be very high. This same device cannot reach the common people at cheap cost, at cheaper price. Today you see we are getting these electronic gadgets almost free of cost, we can say, as compared to 15 years back, 15-20 years back, is not it? Today we are getting a mobile set within 1000 rupees. Can you imagine the situation say 10 years or 5 years, even 5 years back? Where from these are coming? That means the cost is involved. That means it contains some devices, chips. If it is really expensive for its making, that is not possible. So, today these are possible only because of these organic semiconductors, which is easy to prepare, easy to process. So, the cost is less, stable. So, and these are versatile. So, these polymers could be highly promising for many technological uses because of their chemical versatility, stability, processability and low cost. If I show you the application, look at this conducting polymer, how many different applications today, although this is old, this is not today's, say 2-3 years back I could get it from somewhere. So, there are further additions to this list, different types of applications you can find from this conducting polymers. What not today? Because of its versatility, because of its flexibility to prepare, because of its good processability, easy processability, because of its stability, etc., and unique properties, unusual properties which is not always found with inorganic semiconductors. Now, let us see this one. You see, you just compare the conductivity properties, conductivity and specific gravity of metals and organic molecules. See here silver conductivity is 10 to the power 6, just Siemens per centimeter, unit is not shown here. Copper 6 into 10 to the power 5, aluminum 4 into 10 to the power 5, polyacetylene in doped condition almost it has achieved the metallic conductivity. You see, it has achieved the metallic conductivity, polyacetylene, and platinum 10 to the power 5. So, in between this your polyacetylene and polythiophene, the place of platinum is in between these two, 10 to the power 4 doped, 200 undoped conductivity, and look at the specific gravity. The specific gravity has come down. So, the device become lighter, cheaper, stable and highly conducting and easy to make it. But you have to do, how to do? Because if there is problem, whenever you are going to make this conducting polymer device, you have to keep in mind that the other characteristics of polymers are achieved. That means, there are various variables, different variables of stability, molecular weight, molecular alignment, crystallinity, and this what is that called oxidation state of the polymer, and carrier concentration, their mobility characteristics, all these things, those semiconductor properties, those things you have to keep in mind. Then polypyrrole, you see 600. Now, here you see this is polyacetylene, this conjugated system of pi electrons. So, conjugated system of pi electrons. Then here also in polythiophene, single bond, double bond, single bond, double bond, again another in the next unit double bond is there. So, this way conjugated system of pi electron is there. Now, polyacetylene is shown like this, but actually polyacetylene have two stereoisomeric forms. Sorry, like this. You can place the double bond either here or here like this. This is cis form, and transform you practice at home. Conductivity of mercury, ten to the power 4. Then see carbon fiber, organic material. What is carbon fiber? That is graphitized carbon, that is graphitic form. That means it contains sp2 hybridized carbons. So, there is labile electron, so that helps in conduction. So, you can have a thin graphite film, very thin graphite film, graphite thin film for a coating. So, today carbon nanotubes, people are dancing with carbon nanotubes, single walled, multi walled. Somebody is telling multi wall, somebody is telling multi wall, either multi wall or multi wall, up to you. Okay. Nanotubes, these are reactive modified carbon nanotubes. They are having this graphite hexagonal rings with sp2 hybridization, single free electron. Now, if you can make organized thin film of graphite, it is highly conducting, and that conductivity suits our purpose. That can be used in sensor, that can be used in LEDs and many devices. I do not know, my knowledge is very limited over there, in those devices, names of those devices, the functioning of those devices, but I know this material and how to prepare those materials I know. At least if I try, I can make. People are making carbon nanotubes, but it looks like particle, you see, it looks like particle. That means, what is the L by D aspect ratio? So, more is the L by D, more will be the nano effect, more will be the nano effect, and if you can make some device with this carbon nanotube, then that is semiconducting in nature. So, carbon fiber, and you see in my lab there is carbon fiber. You can see that carbon fiber is made from a precursor polymer. What is that precursor polymer? PAN, polyacrylonitrile, that is converted to PAN. People have made carbon fiber from phenolic resins also. I have seen report that people have made carbon fiber from natural fibers, from phenolic resins. Carbon black field polyethylene conducting. Now, I told you a grade of carbon black, 3 grades I mentioned: thermal black, furnace black and channel black. Now, channel black is conducting in nature. Conducting in nature means it may not be very high conducting, but it shows some conductivity value. Why it is conducting? Because if you look into the manufacturing process of carbon black, how it is done? It is made from either natural gas or petroleum oil by controlled by heating at high temperature of, say, it may be 1000 to 1400 degree Celsius in controlled supply of air or oxygen, or sometimes in absence of oxygen. That means, it is a case of pyrolysis. Pyrolysis means carbon hydrogen bond is pyrolyzed. Hydrocarbon, petroleum is hydrocarbon. If that carbon hydrogen bond is pyrolyzed, sometimes carbon carbon bond is pyrolyzed, what happens? There are plenty of your infinite number of free radicals produced. Now, those free radicals combine, interact in such a way, depending on the conditions of that manufacturing process, what happens? They forms this graphite rings there, expelling hydrogen. Okay. More the graphitic effect, more will be the conductivity, more will be the strength of the carbon fiber, more will be the strength of the carbon black particle, and if those are used in rubber compound, in plastic compound, that becomes conducting. So, if you make some polymer composite, if you want to develop some anti-static properties there, then you will add little bit of carbon, although you have to sacrifice the color. If you add little bit of carbon, it will be black. You cannot develop any other color other than black. So, if you can sacrifice color, carbon black is the best one. And to protect from UV degradation, use little bit of carbon black, that will protect the product from UV degradation. Look at polytetrafluoroethylene, it is a perfect conductor or insulator, you can say. Conductivity is almost that is in the insulator range 10 to the power minus 8 order, 18 order. Polyethylene 10 to the power minus 22. Polyaniline has come down to 10. Okay. Polyaniline is a very good conducting polymer, but polyacetylene is the best one till now known. You can increase the conductivity of polyaniline further from 10 Siemens per centimeter to that of towards that of polyacetylene by using suitable dopant. The thing is I was telling you, if you consider this diagram, this one, this diagram, electron cloud. Okay. So, if you can make some device, so that either you can pump electron to this system, or you can suck electron from the system. In both the cases, it will become conducting, either pumping in or sucking out. That means, by donating electron, donor effect, or by accepting electron, acceptor effect. These are nothing but doping, dopants does this function, donor, acceptor. Polyparaphenylene, some formulas are given over here, polyphenylene vinylene, polyparaphenylene sulphide, polyisothionaphthene or naphthene, isothionaphthene. Actually, this double bond is not there, it is mistake, only sulfur atom is there. Sulfur is linked to this carbon and this carbon, the double bond is not there. Okay. There is a mistake, polyisothionaphthene. Now, these are very easy to draw the formula on paper on board, but difficult to synthesize, because once these polymers are formed, it becomes insoluble and infusible. How to process? For example, you take, if you can try in your lab class. In my lab, aniline is available. In my lab, ammonium persulfate is available, APS. You take aniline, add few crystals of ammonium persulfate, within a minute you will find that green to black colored precipitates have been formed. That means, you are successful to synthesize polyaniline. You filter it, wash it, you try to find out the conductivity, you will get the conductivity of polyaniline undoped. Of course, you have to take acid medium, you have to do it in acid medium, HCl, dilute HCl, you take aniline in dilute HCl, add ammonium persulfate, you will get polyaniline, filter it and then make a pellet, measure the conductivity, you will find that conductivity you have got 10 to the power minus 4 order of conductivity you can achieve from there. But how to make a device? If you have to make a device, then either you have to dissolve this polymer in a suitable solvent, you have to prepare a solution, so that from that solution you can cast a thin film over a substrate, or by heating you can melt. On melting you can form a thin film or coating over a substrate, say wafer, silicon wafer, you can make a film, but it does not melt, it does not dissolve, Normally, the polyaniline which is formed in acid medium, it is a salt known as emeraldine salt. Okay. That emeraldine salt is insoluble. Now, you put that polyaniline salt, since it is synthesized in HCl, it will form a salt. Here you see this nitrogen is bonded to hydrogen, here it will form like amine salt, aniline hydrochloride, like aniline hydrochloride. Okay. And that by virtue of that salt formation, it actually does the protonation. That means, this nitrogen will be protonated. This nitrogen will be protonated. Once this nitrogen is protonated, that means that has influence on these conjugated electrons, that helps in conductivity. Okay. Then you take that emeraldine salt, put in some base, means ammonia solution. So, it will be converted to base form, means HCl is removed from there. Now, that base form is soluble in organic solvent, but base form is not conducting, base form is not conducting. So, that will form that base form of polyaniline is soluble in say dimethyl acetamide, soluble in dimethyl formamide, dimethyl sulfoxide, this is soluble depending on the molecular weight of the polymer. All right. So, after dissolving that base form, you take the solution, cast a film on a substrate, then you re-expose that film to some acid vapor or immerse in acid solution. What will happen? It will be again converted to salt. That means, in other way you are converting that polyaniline base film to polyaniline salt by doping of HCl. Now, there you do not have to take always hydrochloric acid, you can take other acids, other organic acids, say paratoluene sulfonic acid, camphor sulfonic acid, chlorosulfonic acid, you can take sulfuric acid. Okay. You can take different acids, depending on their dissociation constant of those acids, you will get different doping effect. All right. Now, this process of synthesis, conversion to base, formation of film, redoping, these are all tricky process. That means, here is the skill of your finger, skill of your mind, skill of your technique, skill of your what is called setup, sophistication of your setup, all these things, all those parameters add to the conductivity of the polyaniline. Somebody is getting a conductivity of 10 or even 10 to the power 2 from polyaniline. How? They could prepare a very organized film, because you see, you think of molecular organization. Suppose this is a layer of polymer. Consider an imaginary plane of a single molecular chain, okay, like this in one plane. Then what happens in a solid state device? What you are having? You are having another plane, stacking one plane over another plane like this in a solid state device. So, in one plane there is one molecule, top of this plane another molecule, top of that plane another molecule. That means, you are stacking molecules one over the other, one over the other. So, this is an imaginary system, imaginary stacking, ideal system. There what happens? Now, if you consider one individual polyanilyl molecule or polyacetyl molecule as a conductor. So, it has got two ends, So, you can tie these two ends to your device, so that or apply some potential, electron flows from one end to the other. So, it can behave like a conductor. Now, it looks like a bare conductor, is not it? Polyanyl molecule polyacrylamide looks like a bare conductor. Now, over one bare conductor you are adding another bare conductor. It is like that of an wire having multi strand, means say 30 thin wires, 30 numbers of thin wires in a bundle of thin wires for passing high current, is not it? So, depending on the diameter of the wire, we see diameter of the wire affects the conductivity, current flow, resistance, all these things. Now, the concept of resistance, resistivity, all these things are coming. That means, if there is scattering of the carrier, during your mobile or during mobility, what happens? We actually sacrifice the conductivity of the material. So, what should we do? Now, in electric fan, electric motors, what you see? There are two coils, armature coil and field coil, and the efficiency of a fan, how fast it can rotate with high RPM at low consumption of energy, that depends on the length of the wire, or the capacity of a motor depends on the length of the wire which is included, that means number of turns. If number of turns is more, then it becomes high capacity. So, that depends on the length of the wire. So, how it is that? How it is done? Actually, it is insulated by enameling. Thin coating of insulating polymers are covered on that conductor. So, those are not bare conductors. So, it is coated. So, in case of conducting polymer, we cannot do that. If one can, marvelous things. That means, core is conducting, there is a cell covering that conductor which can function like insulator. Ideal situation, think of. Okay. Core is conductor, covering is insulator. Then this kind of problem may not occur. So, but when we are making a film, we are doing very in a crude way. Thin film, we are talking about thin film. What is the thickness? Sir, thickness is 500 micron. Is that a thin film? Sir, 100 micron. Is that a thin film? No. If it is of the order of say 10 to 50 nanometer, you can say it is thin film. How to deposit that thin film? How to cast that thin film from a solution? It is not a very simple thing. It is a tricky process, very tricky process. So, if we can do that, then the stacking effect or the problem arising out of stacking effect can be minimized, because what happens during such film formation, one molecule from the lower plane can pass through the upper plane. So, this way that is a random, what is that called, alignment, that means proper alignment is not there. Although, if there are 3 imaginary planes, if you can make that way in such a way that all the molecules in the first plane are lying in the first plane itself, then all the molecules in the second plane lying in the second plane itself, all the molecules in the third plane lying in the third plane itself. That means, no molecule from the first plane penetrates to the medium plane, to the middle plane, to the top plane. If that can be prevented, then we can get higher conductivity, excellent properties. That means molecular alignment, that means it is related to crystallinity, molecular order, is not it? Otherwise, there will be short circuit. Theoretically, we are telling that electron a cloud is delocalized, that means it is in this direction, but we do not bother to think in the other direction also, conductivity in the other direction. These discussions you may not get in books, these are basic fundamentals that you have to think, looking at the final effects, final properties.
So, then how unidirectional conductivity is achieved? If the conductor can conduct in both the directions, then
Apply some insulator, cover with some insulator, cover with some insulator. Say superconductor, people put lot of efforts to develop superconductors, means zero resistance. Today in Kolaghat station, thermal power station is there, in Kolaghat thermal power station is there, power is generated there, and high voltage is required for transmission of power from that place to other places. Say from Kolaghat to Kharagpur, so it needs a suppose 30,000 volt or 40,000 volt. Okay. There is heavy power loss, energy loss while it is passing, transmitting. Now, that power loss could be minimized, we can save money if that power loss is not there, if there is no resistance. Since there is resistance, then we are getting this power at low voltage here, but for getting power at this low voltage, we have to transmit from there at such high voltage, otherwise one cannot get. Think of a pump. Suppose you have a reservoir in this building. Now, if you want to carry water from this reservoir to material science center, you have to have a pipeline and you have to have a efficient pump which will pump water from this building to the building in material science center, and you need a pipeline. And if the inner wall of the pipeline is rough, there will be drag, viscous drag that needs high pressure. So, you have to pump this water from a high pressure, that means high voltage, high pressure, high voltage, that then only you can get adequate flow there. Same thing is in the case of this electrical conductivity. So, superconductor, people thought of superconductor, but people could not achieve it at this ambient temperature. People could achieve say 125 or 150 Kelvin, and that too highly expensive, it is not affordable. Today we get highly scared for our domestic wiring. After construction of a house, for wiring we try to investigate how much cost it will incur for wiring. Sometimes we do not go for concealed wiring, we say no, it will incur more cost. So, if we are scared about that cost, then how can we afford this superconductor price? But there is a scope to develop superconductor which can give you room temperature conductivity, high conductivity, zero resistance, then that will be really remarkable achievement. For that huge power station is not necessary. Okay. And in case of conducting polymers, if we look into conducting polymer structure, theoretically we can think, theoretically we can write on paper, but we have to know, we you have to find out, you have to discover that process or technology, how we can make organized molecules, organized conductor, so that we can get very good conductivity. For this, people have tried with different materials. That means, these are all disturbing elements. These are all disturbing elements. Like phosphorus in silicon, iodine, bromine, lithium, sodium, acidic pentafluoride, ferrous, ferric salts, these things, chlorate, acids, the protons, all these things. These are doping materials for different polymers. People have tried, and you see their range of conductivity, order of conductivity, which could be achieved. Today, millions of people are working in this conducting polymer area. How to synthesize? There are various techniques people are following, out of which 3 techniques are very important. One is chemical polymerization, chemical synthesis, the other is electrochemical polymerization, the third is plasma polymerization, plasma deposition, and CVT, of course, chemical vapor deposition, those things are there, but those needs sophisticated. Suppose you are working, you are a research scholar, you are working with somebody, some of your supervisor, in his lab the CVT facility is not there. CVT facility is expensive today. If there is no CVT facility, can we not do research on conducting polymer? Yes, you can do. You have to go through other techniques of conducting polymer synthesis. In our department, one of our MTech student, your senior, he developed a small unit, plasma unit. He fabricated that plasma unit, and it was run. Plasma was generated using some monomer and benzene also. He got thin film, he measured the conductivity. So, that unit is lying in the MTech lab, in our MTech lab, you can see. So, if you do not have even a plasma unit, you can fabricate it. What is plasma unit? You can have electric plasma, chemical plasma like this. That means, you have to get some ions or free radicals, activated species. You take a material, suppose you can take it to its plasma state. That means, you have to energize this material to such a level, so that its bonds are ruptured in such a way that smallest units are separated from each other, and they are very much activated. If you can take it to that activated state, then if there is a suitable substrate, on that substrate those activated species can be deposited. That is a plasma deposited film of this material. So, if you start with a monomer, say acetylene, if you start with aniline, if you start with pyrrole, if you start with thiophene, you can get polyaniline, polythiophene, polypyrrole films on a substrate. Says if you take a silicon wafer, if you keep that silicon wafer in that plasma chamber, and when those monomers are taken, of course, it is a very low concentration plasma. So, those will be activated to that plasma condition, activated species in the form of radicals and ions will be formed, and then they will interact with each other. After interacting, they will form some solid material, and that solid material will be deposited on the substrate. So, you can get a plasma deposited thin film of that polymer. And chemical synthesis I have told, and electrochemical synthesis, you have to take a cell with two suitable electrodes, take the monomer on one of the electrodes, this polymer will be deposited after electrochemical polymerization, provided they have redox behavior. Otherwise, the electrochemical polymerization cannot be successful. Okay. So, these are the various techniques for your synthesis of conducting polymers. Today, let us remain here. Thank you very much.